I would, before we get into our problem, and you're like, whoa, before we do our problem, I thought we always start with our problem. I just want to mention something about concavity. So last time we talked about concavity, which has to deal with the second derivative, and it talks to us about information about what the function is doing. And I just want to motivate a little bit more about what we can learn from concavity. So here's sort of something, an idea of sorts. And here we go. So we know if I have a curve y equals f of x, then I can talk about at my point, I have a, and I have f of a. Well, one of the things we said, okay, so we know that we can talk about the value of the function at a point. That gives us some information. And then we said, well, the next level up is to get the derivative. And if I have the derivative, what can I get? Slope, but slope of what? Slope of the tangent line is what we're after. So if I have just the value of the function, I get a point. If I have the derivative, well, what I get is I can now get a tangent line, which is an approximator. So the tangent line gives us information about what's happening sort of locally with the function. What can you get from the second derivative that helps you go a little bit further? Well, the answer is, if you know a little bit about the second derivative, you can talk about how the function is behaving in relationship to the tangent line. And here's the idea. So if your second derivative is positive, so that says if f double prime, if that's positive, we call that concave up. Now, for us, what that means, if we are positive, the function will actually come up from the tangent line. So concave up, the function is coming up off the tangent line, on the up side. So concave up. On the other hand, if our function is f double prime negative, well, we call that concave down. And what that means is that the function is coming down off the tangent line. So concave down. And now, as I write this, I realize I probably shouldn't have chosen red and green because there are people who can't distinguish between red and green. I actually have a co-author who I work with who is red-green colorblind, but he's famous for his papers on coloring. Well, the great ironies of life. All right. So that's sort of something you can extract from the concavity information. If you go back to our second derivative test, it makes sense now, because remember, the second derivative test, the idea was the tangent line was equal to a flat line, because that was where the derivative equals 0. So now, if you think about concavity, what's happening? If you're concave up, that means you're coming up on the positive side. While if you're concave down, then you're going to go down on the negative side. And that sort of emphasizes how the second derivative test works. Okay. So I just wanted to mention that. So our problem. So this comes from a final exam from a few years ago. It was a fun final exam. I really liked it. And I think we actually got a couple of grad students breaking down in tears after they took this test. So I know it was a good test. Given the sketch of f prime of x below, give a sketch of f double prime of x. So okay, so we have the curve f prime. Now, we had to, when we did this exam, we said it explicitly like 3 times. This is the derivative, this is the derivative, this is the derivative. Students didn't quite pick up on that, but hopefully we can understand that that prime means it's the derivative. Now, if I want to sketch f double prime, first thing I should do is draw a set of axes. Okay, so there we go. That's not so bad. And we don't have to be perfect. We just have to be reasonable. We think, okay, how does f double prime relate to f prime? Well, what's the answer? How do I get from f prime to f double prime? Take the derivative. So we start looking and saying, okay, what are interesting points for the derivative? Now for us, sort of our key thing to go off of is look for places where your derivative is 0. In other words, you're looking for places where you'd have a flat line, which would be tangent to your graph. So there's a couple places that pop out. Notice that, particularly at -1 and -3, the line that would be tangent to that graph would be 0, which means that were we to take the derivative at -1, we would get 0. And were we to take it at -3, we would get 0. So we know for sure that the curve has to pass through these 2 points. Now we sort of say, okay, let's think about the sign. Well, let's talk about between -3 and -1. If we just sketch a quick tangent line, what's true about the slope? Is it going up or down? It's going up, which means it's a positive slope, which means I've got to do something positive. That's a rough estimate. Okay, how about, say, after -1, what's happening with the slope? It's going to be negative because we go down. So we're going to go down. Okay, how about before -3? What's happening? It's going to go down again, which means I have to have a negative. Because the values here are telling me about the slope. Slope equals 0 at -3 and -1. Slope is positive because I'm going up. Slope is negative, I'm going down. So going down, negative. Going down, negative. And that's good enough. We just need really a rough sketch. The full instructions for the exam said, just make sure you get the zeros right and you get the signs right. And you get full credit. Because, without more information, we can't do much more beyond that. So that was part 1. Now, let's identify the intervals where f of x is increasing and decreasing. If I want to understand increasing and decreasing, do I look at f prime or do I look at f double prime? I'll write f double prime for reference. Which one tells me about increasing or decreasing? F prime does. So f prime talks about whether the function is increasing or decreasing. So what am I looking for? Increasing corresponds to what? F prime is positive. So increasing is code word for saying f prime is positive. What about decreasing? F prime is negative. So we look at the picture and we say, okay, when is f prime positive? So that says I want to be above the axis. So the answer, when is f prime positive? Well, up to 1. So I'm increasing for x less than 1. Or I like to say x less than or equal to 1. And then we're decreasing, that would be where we're negative, if we're greater than or equal to 1. Okay, so that's part 2. Part 3. Identify and classify the x-coordinate of any critical points. Well, there's no boundary, because there's no end. These little arrows here means that the curve continues in whatever it's currently doing. So there's no boundary, so that's not a critical point. Is our derivative ever undefined? No, there's a question though.
Why would it be greater than or equal to and less than or equal to if we're just greater than and less than?
Why is it greater than or equal to instead of just greater than? Well, I see somebody has read the book. Okay. The reason is if you go to the definition of increasing and decreasing, we think about increasing, we can't really say something is increasing at a single point. Increasing is always about comparisons. So I want to compare things. So I'm increasing in an interval is if I compare 2 points in that interval, the one, say, it's hard to draw a picture. Okay, let's see. So this is increasing. So I'm increasing if I pick 2 values A and B and I compare the outputs. If f of A is smaller than f of B, given that A comes before B. That's the definition of increasing. Which means I can include endpoints. We'll do a really simple example. Let's take x squared. Where is x squared increasing? Now, people will say, the question is, do we include 0? So I'm going to say, let's talk about 0. If I compare 0 to anything else, what's true? Well, am I below it, the output? And the answer is yes, I am below it in the output. And so because I'm below it in the output, I'm satisfying the rule that whenever I make a comparison, the one that comes first in the ordering of the inputs also comes first in the ordering of the outputs. And so because I'm satisfying that rule, that's why we include the endpoints. Now, that's me. You can go ask other calc instructors and you might get different opinions. And now you're probably saying, but wait a second, I thought math was beautiful and perfect and no one disagreed. Well, the parts that we show you. But there are parts where it's like, what do you really mean by that? And so as a consequence, you might get different opinions. And here's the thing to remember. We're not going to nitpick you on the endpoints. Whether you include it or not, you'd get the full credit. But that's why I include it. Okay, back to this. The x-coordinate, we talked about there's no boundary points. Is the derivative ever undefined? Well, no, because it's there. We see it all. So what's left? So what kind of critical point can we look for? Where the derivative equals 0. So we say, okay, is the derivative equal to 0? Well, that would be where I cross the axis. And that's a place where I cross the axis. So there is a critical point. So we have a critical point at x equals positive 1. Because that's where the derivative is equal to 0. What kind of critical point is it? Is it a max, or is it a min, or is it neither? It is a max. How do we get max? Because you might say, that's not a max. But remember, you're looking at it through f of x colored glasses. You've got to take your f of x colored glasses off. This is f prime of x. So think about what's happening to f prime. If I'm below 1, what's the sign of f prime? If I'm below 1, the sign of f prime? The sign of f prime is positive. The function is positive. If I'm after 1, what's the sign of f prime? Negative. So that means I'm coming up to the left, down to the right. So I'm coming up from below 1, down after 1, and therefore it's a maximum. Okay, number 4. Identify the intervals where f of x is concave up and concave down. If I want concavity, where do I look? Do I look at f prime or f double prime? F double prime. So when I'm looking for concavity, concave up, what does that correspond to? F double prime is positive, concave down? F double prime is negative. So we're looking at our second derivative. When is the second derivative positive? I should have marked these numbers here for reference. Negative 3 to negative 1, that's when we're positive for our second derivative. So concave up, negative 3 less than or equal to x less than or equal to negative 1. When are we negative? Well, every other time. So if we are below negative 3 or if we are above negative 1. Now the last part, number 5, says identify the x-coordinate of any inflection points. So where do we find inflection points? That's the second derivative. What are we looking for? The second derivative equals 0 is a place where we check. In particular, when we're looking for inflection points, we're looking for concavity changing. So we can do it without the picture. We can actually look here. But for the picture, it's easy to spot. Because there's two places where we're going to have a change in behavior. At negative 3, we're changing from f double prime being negative to f double prime being positive, or concave down to concave up. So negative 3. And then at negative 1, we're changing from f double prime being positive to f double prime being negative, concave up to concave down, which means that we also include negative 1. So those are the x-coordinates of the inflection points. Now you might say, do we have different names for these? And the answer is no, we don't distinguish. Whether we go from concave up to concave down or vice versa, we just say it's an inflection point. So that's as far as we go. All right, well, that's the review. Now for today. What's today? Well, today It's a wonderful day because it's the return of 0 over 0. Just when we thought we were done, it pulls us back in. All right. Now you might remember 0 over 0 because we got to do a lot of the fun things. We said, well, whenever you see 0 over 0, it means more work, more work. Of course, when we did that, it's because 0 over 0, do you remember what was the problem with 0 over 0? It was undefined because it was ambiguous. See, 0 over 0 could be anything. Now, ambiguous sounds too nice and conversational. So we had to come up with a more complicated word which we couldn't spell. So it's also called indeterminate, which means that we don't know what it is. You can't determine the value just from the expression alone. You have to use additional information. Now, 0 over 0 is the classic form of being indeterminate, but we also have, of course, infinity classic, which is infinity over infinity. But it doesn't stop there. There's lots of things which are like this, expressions which we cannot figure out what they should be. Examples include infinity minus infinity, 0 times infinity, 0 to the 0, and 1 to the infinity. All of these expressions cannot be determined just from that form. What is 0 to the 0? Well, it depends on what that means. It could be anything. What is 1 to the infinity? Well, again, it depends on what that means. I know you want to say, well, it's equal to 1. Well, but is it? It's hard to say. Now, we learned how to handle a few cases, but that was back before we had lots of good tools. We have more tools, better tools. In particular, we have the derivatives. And now we're going to say, okay, can we use derivatives to help us answer some of these limits? And the answer is yes. Yes, we can. And the way we do it, there's something wonderful rule called L'Hopital. Now, you just have to sort of channel your inner French, you know, oh, L'Hopital, oh, you know, and be like, okay, what is L'Hopital? L'Hopital. All right. So, here's what it is. Suppose you have the following. You have a function f and a function g, and they're nice functions in the sense that I can take derivatives. And in particular, derivatives at a point A. We'll explain what we mean by A in a second. And the limit as x approaches A, okay, so here we go. That's what A is. Of f of x over g of x goes to 0 over 0 or infinity over infinity. Either one doesn't matter. And it turns out that the limit of f prime over g prime exists. If all these things are true, then you have the following fact. That the limit as x approaches A of f of x over g of x is the same as the limit as x approaches A of f prime of x over g prime of x. So this is nice. Now, you might say, why is it nice? Well, f of x over g of x might be complicated, but f prime over g prime might not. In the following sense, f of x over g of x might have a 0 over 0, but f prime over g prime doesn't. And so it's much easier to take the limit. And so what we have is the chance to say by taking these derivatives of the top and over the derivative of the bottom, that we'll get something which is easier to take the limit of. Now, you have to be careful here, because it feels like, oh, I have a fraction, I'm taking derivatives, so you want to use the quotient rule. This is not the quotient rule. So remember the quotient rule says you take, the low, d high, minus high, d low, and then you fill up half a page. It's much simpler than that. It's literally the derivative of the top divided by the derivative of the bottom. You take those derivatives separately, and that gives you your answer. All right, so that's L'Hopital. Now I will say there are a couple different spellings of L'Hopital. This is more of the La Hospital type of spelling. Sometimes you'll also see it, because it's French, with a little accent mark, L'Hopital. You know, it just depends. As you can tell, I don't speak much French, but that's all right. I know enough to get by. So, we're going to just do a bunch of examples. And once you get the hang of it, they're all going to be sort of very similar. We're going to say, okay, is this something indeterminate? If it is, let's apply L'Hopital. So we'll start with some easy examples, and then we'll get to more interesting ones. All right. So find the limit as theta goes to 0 of 3 theta minus sine theta over theta. Okay. So let's just check. So what does this go to currently? If we plug in 0, what do we get on the top? 0. If we plug in 0 downstairs, what do we get? 0. So it goes to 0 over 0. That's good. Are these functions differentiable? Yeah, so they're nice. So that means we've satisfied most of the requirements of L'Hopital. So we say, okay, so we're going to apply L'Hopital, mon ami, and I'm going to mark an LH just so I know that I'm applying L'Hopital. Now, if you apply L'Hopital, you need to do at least 2 things to apply it if you want to get credit on an exam. Now, if you don't want credit on the exam, you like to live dangerously, then don't pay attention to what I'm about to say. The 2 things you need to do are, 1, somehow indicate that you're taking L'Hopital, which is why I put the LH, or you could just say, apply L'Hopital. The second thing is you have to verify that you can use L'Hopital, which means you check to see that it goes to 0 over 0 or some other related form. If you omit one of those 2 things, you might lose points. And of course, our goal, got to get them all. What's the derivative of the top? 3 minus cosine theta over the derivative of the bottom? 1. Now, can we take this limit? Yeah, because this is great. This is like, we'd say game over. Why is it game over? Well, look at your denominator. What do you see? You see a 1, which is not 0. And so now it's just plug it in and let's see what we get. What do you get when you plug in theta equals 0? You get 2. And now we're done. Now, we should actually note, we could have done this limit without L'Hopital, because what can we do? Well, 3 theta minus sine theta over theta, I can rewrite that as 3 theta over theta, which is 3, minus sine theta over theta. And the thing is, we know what happens to 3. 3 turns out it goes to 3. What about sine theta over theta? What does that do? Goes to 1. So it goes to 3 minus 1, which is 2. Notice, it's the same. But this might feel a little bit easier to do L'Hopital. Okay, how about this one? Find the limit as t goes to 0, sine of 5t, divided by e to the 2t minus 1. All right, well, let's check to see if we need to do anything. What happens when we plug in t equals 0 on the top? Get sine of 0, which is 0. What happens when we plug t equals 0 on the bottom? We get 0 again. L'Hopital. So we're going to apply L'Hopital. Okay, so it's still a limit, because there's still the limit, but now we take the derivatives. Derivative of sine of 5t. 5 cosine 5t, got to apply your rules, in this case the chain rule, over, derivative of the bottom? 2e to the 2t. Again, the 2 comes down, and the minus 1 goes away. Now, what happens here? Well, plug in 0. What do you get in the top? 5, which means it's game over, right? As soon as it's not 0, we're done. What happens downstairs? What do we get? 2. And we're done. And you're probably thinking right now, why didn't you start with this? This is so much better. I love this a lot more. All right, I understand how you feel. But the reason we couldn't start with this is you have to first build up the machinery. So we couldn't use L'Hopital, for example, to do sine theta over theta, because in order to take the derivative of sine theta, you have to know what sine theta over theta does. So unfortunately, we couldn't start with this until we had our machinery in place. But now we do, which means from here on out, for the rest of the semester, L'Hopital. Oh, good stuff. Now, The thing is, we might like L'Hopital so much, we're saying, let's not do it just one time. Let's do it more than one time. In fact, you can keep going as long as you like. No problem. No problem. Okay, so let's try. What happens when I plug in 0? Upstairs, what do you get? You're going to get 0 minus 0, which is 0. Downstairs, what do you get? 0 minus 0, which is 0. Which means we need to do more work. And of course, our more work, L'Hopital. Oh, L'Hopital. Mon ami. Mon ami. Okay. So we're going to apply L'Hopital. Limit as x goes to 0 of, okay? Got to take the derivative of the top and the bottom. Well, let's take the top first. Derivative of x, 1. Derivative of minus 1/2 sine of 2x. Yeah, it'll be a cosine of 2x. The 2 is going to come out and cancel with the half. Is it plus or minus? Minus. Okay. Downstairs, what do we get? Secant squared x minus 1. Now, plug in 0. Upstairs, what do you get? Well, 1 minus cosine of 0, which is 0. Uh-oh. Downstairs, what do we get? Well, what's secant of 0? Secant of 0 is 1. We get 1 minus 1, which is 0. Which means what? More work. Good. You're catching on. And what's the more work? Oh, L'Hopital. Okay. We keep going. Limit as x goes to 0. Okay. The derivative of the top. What is that going to give us? 2 sine of 2x. Derivative of the bottom. Okay. Derivative of secant squared. Well, that's 2 times secant x to the 1 times derivative of secant, which is, well, derivative of secant is secant times tangent. So times secant x tangent x. Okay, I'll clean that up a little bit downstairs just because I see there's 2 secants. We might as well put those 2 together. 2 sine of 2x divided by 2 secant squared of x tangent of x. Now, what does the top go to? 0. What does the bottom go to? 0. What does that mean? More work. Oh, what a wonderful problem. Okay. Equals. Oh, L'Hopital. Okay. Limit. X goes to 0. What's the derivative of 2 sine of 2x? 4 cosine of 2x. Now, game over, because that's not going to go to 0. Downstairs. Okay, got to do some product rule here. So the derivative of the first part, so that'll be the derivative of, well, think of it, secant squared x. The 2 secant of x times secant of x tangent of x times this other tangent of x that's already there. So this is the derivative of the secant squared plus, oh my gosh, I'm going to run out of space, 2 the secant squared of x times the derivative of tangent of x, which is another secant squared of x. Okay, well, I'm glad it's over because I don't think I'd want to go another round. All right, now, what happens? You plug it in. Upstairs, you get 4. Downstairs, well, the tangent of 0 is very useful. That means all that stuff goes away. Secant of 0 is still 1, which means you get 2. 4 over 2 is 2. All right. Good. In fact, it's not so hard to construct examples of L'Hopital where you get to go many, many rounds. Good times. Looking forward to all the creative things we can do. Let's do something a little bit more abstract for right now. Suppose we're given that f of x is twice differentiable, which means I can take 2 derivatives. I want to find the limit as h goes to 0 of f of x plus h minus 2 times f of x plus f of x minus h all over h squared. Okay. Well, let's plug in 0. If we plug in 0, what do we get downstairs? We'll start with that one. That one's easy to spot. We get 0. Upstairs, we'll get, what's the first term? F of f of x. The second term? 2f of x being subtracted. The last term is f of x being added. But notice what happens upstairs. Yeah, so it's 0 over 0. So what do we do? L'hôpital. Ah, l'hôpital. Okay, so this is by l'hôpital. Limit as h goes to 0 of, let's go through, what's the root of the first? F prime of x plus h. What's the next term? Is it negative 2f prime of x? Or is it something else? What do you think the next term should be? What happens when we take the derivative of 2f of x? What do we get? We get 0. What? What? 0? Where's the 0 coming from? What's our limit? Limit is h goes to 0. So what's acting as the thing that's varying? H is the varying part. X is just x. It's fixed. So when I'm thinking of taking the derivative, I'm thinking of taking the derivative with respect to h. It's whatever you're taking the limit of. That's the thing that you take the derivative. So when we get to 2 f of x, because there's no h, it's gone. Well, that's nice. How about the derivative of f of x minus h? What is that? F prime of x minus h. But, chain rule, what do you have to do? You have to put a negative, because the derivative of x minus h, because we're taking the derivative with respect to h, would be a minus 1. So instead of being a plus, it's a minus. Okay, the derivative of the bottom? 2h. All right, now let's see what this goes to. This goes to, downstairs, we get 2 times 0, which is 0. Upstairs, what do we get? Well, f prime of x minus f prime of x, which is still 0 over 0. So what do we do now? Do it again. L'hôpital. Oh, okay. L'hôpital. No, by the way, you don't actually have to make the noise during the exam. You know, it's not like, I reached the l'hôpital problem. Oh, you know. Then everyone will know, like, oh, I'm doing number 5 right now. So, but you can do it mentally. Mentally. Okay. All right. Upstairs. First derivative of the first term will be what? F double prime of x plus h. What's the derivative of the second term going to give us? F double prime of x minus h, but because that minus comes out again, it'll be a plus. Downstairs we get 2. The nice thing is, game over, because that's not going to be 0. So, we end up with f double prime of x, because we're plugging in h equals 0, plus f double prime of x divided by 2, which simplifies to f double prime of x. Now on a side note, you might say, oh, well, this is just a little cute example. But actually, this is used to do data processing. So if you're trying to look at data and say, well, I want to get some information about the second derivative, because second derivative has useful information. The way that it's actually done in a computer is very similar to this. So it's not just a cute example. This is worth money. This is good stuff. All right, and we're just giving it away for free. Now, we've done a lot of 0 over 0, but there's other indeterminate forms. So we want to know, how do we handle the indeterminate forms that aren't 0 over 0? The answer is, you get them to be 0 over 0 or infinity over infinity. Anything that's not of the right form, because you can't apply l'hôpital unless it's of a fraction. So let's look at this example. What happens to y as we approach 0 from above of y log y? Now the reason we're approaching 0 from above is I can't approach 0 from below, because log is not defined for negative values. Now, what happens to y as y goes to 0? Goes to 0. What happens to log of y as you go to 0? Log of y blows up, goes to negative infinity. If you remember what the log function looks like, it looks like this. So as you go to 0, it's trying to shoot down to negative infinity. Okay. So the question is, what is 0 times negative infinity? And the answer is, well, you can't figure it out from just that expression. We need more. We have to have a better tool. So we say, okay, we have our fraction tool of L'Hopital. So we want to make it into a fraction. Now there's two possibilities. One possibility is I could say, look, how do you make a fraction? Well, the answer is you just pick one of the two terms and you move it down. So one thing I could do is I could keep the y upstairs, and then I move the log y downstairs as 1 over log y. Or I could keep the log y upstairs and then move the y down as a 1 over y. Both of these expressions are equivalent to what we started with, and they have the advantage of being a fraction. Now, which one should we use? It may not be immediately obvious which one we use, so we'll just pick one. For instance, suppose that we look here. Limit as y goes to 0 from above. Well, what happens to the top? Goes to 0. What happens downstairs? Goes to 1 over a huge number, which is 0. So this is currently going to 0 over 0, which means L'Hopital. Okay, so we apply L'Hopital. What's the dirt of the top? 1. That's great. What's the dirt of the bottom? Well, now, this really is a fraction within a fraction. You can think of this as log of y to the negative 1. So the derivative of this would be negative 1 log of y to the negative 2 times the derivative of log of y, which is 1 over y. If you clean this up, this becomes the limit as y goes to 0 from above of negative y divided by 1 over log of y squared. Now, comparing it to what we started with, that looks worse. Maybe we chose wrong. So let's make a different choice before we try to go any further. Suppose we did log of y, 1 over y. Well, what does this go to? What's the top? So it's negative infinity, because that's blowing up. How about 1 over y? What does that do? It's 1 over a small number. That's blowing up. It's going to infinity. So I can apply L'Hopital. L'Hopital works. All right. So what can we do? Well, we channel our L'Hopital. L'Hopital. Okay. What's the derivative of log y? 1 over y. What's the derivative of 1 over y? Negative 1 over y squared. Now, clean it up. That's the limit as y goes to 0 from above. And then if I take this 1 over y squared and flip it, move it to the top, it becomes negative y. Now, you'll notice this is nicer. In particular, what's this limit? 0. So it can make a difference on which choice you make. So the question is, how do you know which choice to make? Make the choice which will be easier to have something to take a derivative of. Because you know you're going to have to take a derivative. So whatever you move downstairs, you have to make sure that it's something you can work with. Because if it's not, oh, life is hard. Life is hard. So what are some other things that could happen? Now there's a nice fact that says that limits can pass into continuous functions. And that's not too surprising. In fact, that's one of the things that really defined continuity, was the idea that limits can go inside a continuous function because there's no surprises. So we have that the limit as x approaches a of f of g of x is the same as f as the limit as x approaches a of g of x. Now, how do we use that? Well, the main way we're going to use this is to say, what if you have something in an exponent? So you have this expression here. 1 plus t over x raised to the power x. And I say, I want to take that limit. Now, the problem is, we can't use L'Hopital. It doesn't apply. The other problem is, it's indeterminate. Currently, what's happening to it? Well, what's the inside approaching? 1. What's the exponent approaching? Infinity. And 1 to the infinity, it's not clear what that should mean. It could be almost any number. Okay, so we want to say, all right, we want to get to a point where we can get a fraction. The way we do it is we say logs could help us out. Because with the log, I can pull an exponent down. So, here's the idea. I'm going to temporarily set L, the limit of my expression. So, L is the limit as x goes to infinity, 1 plus t over x to the power x. I take the log of L. So that's log of the limit. And now I use the fact that log, it's a nice function, which means I can take the limit outside of the log. So I can move the limit out of the log of log of 1 plus t over x to the x. Now, what's the property of log that we can use here? Yeah, this x can come down. So, this becomes the limit as x goes to infinity of x natural log of 1 plus t over x. Now, there's good news. There's no longer an x both in the exponent and in the base. What's happening to this limit? Well, currently, we have x, that's going to infinity. This part's going to log of 1. So it's going to infinity times 0. Which means it's what? It's indeterminate. Can we use L'Hopital yet? No. Not yet. What's wrong? Why can't L'Hopital work yet? Got to make a fraction. Now, so we have a choice. Do we move the log down? Don't do that. Don't do that. Or do we move the x down? Yes. Yeah, we're going to move the x down. We learned our lesson from the last example. So this is the limit as x goes to infinity of natural log of 1 plus t over x over 1 over x. Now the upstairs going is to log of 1, which is 0. The downstairs, what does that do? Goes to like 1 over infinity, which is 0. So it's going to 0 over 0. So what can we do? L'Hopital. Ah, L'Hopital, mon ami. Okay. So this is the limit as x goes to infinity. Well, what's the derivative of natural log of 1 plus tx? 1 over 1 plus t over x times, well, t is a constant. What's the derivative of, so t I can just think of as a constant. What's the derivative of 1 over x? Negative 1 over x squared. Now, downstairs is the derivative of 1 over x, which is the same as what we just said, negative 1 over x squared. And now we're like, ooh, nice. The negative 1 over x squareds cancel. So, what do we get? Well, there's only one x left. Let's take our limit. We get t over 1 plus t over x. But t over x, what happens to that? Goes to 0. So that means we get t. Is t our answer? And why not? Okay, so t is not our answer, but it feels like our answer. We got t out. What's wrong with it? Run it back. What does t equal? T is log of our answer. So what if I want my answer? What do? I use the exponential function. Because to get rid of logs, you use the exponential function. So L, That's e to the log of L, which is e to the t. So this shows you that you can get all sorts of strange numbers. I can get e squared. I just choose t equals 2. I can get e to the pi. I can choose t equals pi. I can get all sorts of fun numbers. All right. Let's see. I'm going to jump around a little bit here, because I think there are some good examples here. Find the limit, as x goes to infinity, of x plus sine x over x. Well, what does the top go to? So this is going to infinity over infinity. Because the sine, it's never really changes much. So if I have a huge number plus something that's small between negative 1 and 1, the result's going to be a big number. Okay, so what can we do? Oh, right? Oh, little bit down. Oh. Okay. Limit as x goes to infinity of what's upstairs? Well, 1 plus cosine of x over 1. Now what happens to 1 plus cosine of x over 1? What's that limit as x goes to infinity? So remember, think about what the cosine function does. Cosine is going to do this. It's going to keep going up and down. So what happens to 1 plus cosine x as x goes to infinity? It doesn't go to anything. It keeps moving up and down, up and down. So that limit does not exist. So is that our answer, and why not? Yes, it is our answer. That's a bold move. It's actually not our answer. But you might say, but Steve, I even made the sound when you did that. I totally channeled my inner l'Hopital. What was the problem? Remember that there's an assumption. The limit of f prime over g prime has to exist. If it doesn't exist, it doesn't work. This limit didn't exist, which means we can't apply l'Hopital. But we can do something else. It's called algebra. So if you take this limit, x over x is 1, and sine x over x is sine x over x. Now, what happens to 1? It goes to 1. That's the true statement. Now, what happens to sine x over x? Now, be careful here, because I know you want to channel your sine x over x goes to 1 mentality, but that's when x went to 0. Sine x over x, x is going to infinity. What's happening to that expression? It's going to go to 0. Because what happens is the sine of x on the top doesn't change much. It's always between negative 1 over 1. But the x downstairs changes. It gets big. So it's a small number over a big number. That goes to 0. And therefore, the answer of this limit is 1. So even l'Hopital, even then, there can be struggles. So you got to be careful. Well, we have a couple more problems to work through. So let's do it. Let's do it. Suppose you have the form infinity minus infinity. What do? Well, always the goal is a fraction. Can't do l'Hopital. L'Hopital. Can't do it without a fraction. Now here, you say, okay, what's happening? Well, when you plug in 0, you get 1 over 0. And here, you get 1 over 0. So when you have 1 over 0, that's like infinity minus infinity. Bad. So what can we do? Well, the answer is we can do common denominator. Let's actually write this as a fraction. So that's the limit. T goes to 0. Now the common denominator, I need to have a 3. T squared. So this will need a t and a 3. And this one it needs to have a sine of 3t. So it'll be 3t divided by 3t squared sine of 3t minus, over here, it'll be sine of 3t divided by 3t squared sine of 3t. So this becomes the limit, as t goes to 0, of 3t minus sine of 3t over 3t squared sine of 3t. Now what do we do? Well, let's L'Hopital, right? Because you have 0 over 0. Oh, L'Hopital, L'Hopital. Okay, so we should note, this goes to 0 over 0. This is our justification. Remember, we always need to have somewhere we justify. There's our justification. So L'Hopital, this becomes a limit as t goes to 0. Derivative of the top, that's 3 minus derivative of sine 3t, 3 cosine 3t over the bottom. Well, what'll that be? That's going to be, 3t squared, derivative of that 6t sine of 3t, and then we're going to have plus 3t squared times derivative of sine, which will give 9t squared cosine 3t. Now what does this go to? Well, this is going to go to 0 over 0, right? Because upstairs you get 3 minus 3, which is 0. Downstairs we have a bunch of stuff. And, well, we didn't plan well. That's okay. We'll just continue it on this piece of paper here. All right, so 0 over 0, what do? Well, whenever we see a 0 over 0, L'Hopital, 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 oh, L'Hopital. Okay, so that becomes a limit as t goes to 0. Upstairs, what do we get? Well, derivative of cosine, negative sine. So we're going to get 9 sine 3t. Downstairs, what do we get? Well, we're going to get a lot of stuff. So mostly we're going to get impatient. But no, we're not going to do that. We're just going to work it through. Okay, so what do we get? We get 6 sine of 3t. Then the next term is going to be 6t times the derivative of sine of 3t. Well, that'll be 18t cosine of 3t. Then we go to the next term. Well, again, product rule. There's another 18t cosine 3t. And then we're going to have 9t squared times the derivative of cosine 3t, which will be minus 27t squared cosine 3t. Oh my gosh, we barely cut it on the screen, but it's there. It's all there. All right, well, clean it up a little bit. Limit t goes to 0. One thing we can do is we can certainly divide out by 3 if we wanted to. Might as well. 3 sine 3t. Downstairs, what do we have? Well, we have 2, because remember we divide everything by 3. 18 plus 18 would be 36, but divided by 3 is 12t cosine 3t. And now, minus, then we divided by 3, so minus 9t squared cosine 3t. Well, what does this do? Upstairs, sine of 3t, 0. Sine of 3t, 0. And t is 0. T squared is 0. Lots of zeros here. Well, I guess one thing... Oh, whoops. Ha ha ha. Here we took the derivative of cosine. We should have gotten a sine. Oh my gosh. Good thing we can correct ourselves. There we go. Back in business. Okay, but still, it's going to 0 over 0. Whoa! What do we do? Oh, L'Hopital! Okay, so we're going to do L'Hopital! Wow! This is so cool. L'Hopital. Never leave us, my friend. So, take the derivative. What do we get? 9 cosine 3t. And now we know, game over. Whatever happens, this is the last step. Why? Well, look at it. 9 cosine of 3t. That's not going to 0. So this is fantastic news for us. Let's see what happens downstairs. Well, we're going to get 6 cosine of 3t. Then over here, well, we'll get plus 12 cosine 3t. 12t, or that, plus 12t times root of cosine 3t, which is minus 36t times cosine 3t. Then here, minus 18t sine of 3t. And, oh, I'm going to run off the screen. Okay, and then there's one more. Then there's going to be a minus 27t squared cosine 3t. That goes right there. Wow. Okay, but we're not quite done because we still have to write down the answer. Plug in t equals 0. Upstairs, we get 9. Downstairs, we get 6, because that's going to be 1, plus 12, because that's going to be 1. Then that'll be 0 because of the t. That'll be 0 because of t and sine 3t. That'll also be 0. So 6 plus 12 makes 18. Or 1/2. Wow. There we go. Well, all right. Probably wouldn't have guessed a half. Maybe we're not too surprised, but wouldn't have guessed it. Okay, good. So let's do this other problem. This also involves sort of a form of infinity minus infinity, because what do we see? Well, we see infinity, right? It's going to infinity minus infinity. Now, what do we do? Well, here we can do conjugation. Conjugation can sometimes work. So if you do conjugation, it's square root of z squared plus 4z, and then plus z over square root of z squared plus 4z plus z. Okay, so we're in a different problem. Let's just separate. So this would become here the limit as z goes to plus infinity. Upstairs, we're going to get z squared plus 4z. The square root goes away, minus z squared. And downstairs, we're going to end up with the square root z squared plus 4z and plus z. So be careful here. This square root ends there. All right. Well, that simplifies nicely upstairs. So that's the limit as z goes to infinity. Z squared minus z squared, that's 4z. Downstairs, square root of z squared plus 4z plus z. And now we say, well, what is that doing? Well, it's going to infinity over infinity, because z is going off to infinity. Which means, this is our infinity version of 0, 0. Or like what we said, infinity classic. So, we apply L'Hopital. L'Hopital! All right, L'Hopital, what do you get? So if we apply L'Hopital, so here's our L'Hopital. That's going to be the limit. Z goes towards infinity of upstairs, we get 4 over downstairs. Well, square root of z squared plus 4z is going to be 1/2 z squared plus 4z to the minus 1/2 times the derivative of the inside, which is 2z plus 4, and then plus 1 more. Now, that does not look like it's simplifying quite as much as we were hoping, but let's see. Maybe we can work with this. I'm going to move this up a little bit. So, what does this become? This becomes a limit as z goes to infinity of 4 over, now the half can multiply by 2z plus 4, so what we really have is z plus 2 over the square root of z squared plus 4z, then plus 1. Now, fractions within fractions, that does not work very well. So, this becomes a limit as z goes to infinity. Let's multiply top and bottom by the square root. Oh, that should be a z squared there. Square root z squared plus 4z and a square root of z squared plus 4z, just to get rid of the fractions within fractions. So 4 square root z squared plus 4z. Downstairs we get z plus 2 plus the square root of z squared plus 4z. All right, well, what's this doing? Well, this is going to infinity, and that's going to infinity. So this is currently going to infinity over infinity. All right, so what can we do? Well, we can do l'hôpital. L'hôpital. Okay, so let's see what happens. All right, so we work our process here. That'll be 4. And we've actually taken this derivative before. In fact, we did it right up here. So it's 1/2 z squared plus 4z to the minus a half, then times 2z plus 4. Downstairs, we get, well, derivative of z plus 2 is 1 plus, and again, we're going to get a 1/2 z squared plus 4z to the minus a half times 2z plus 4. All right, well, what can we do? Well, we're going to multiply top and bottom by the square root of z squared plus 4z. Get rid of our fraction, right? Limit as z goes to infinity. Now upstairs, this square root and that square root are going to cancel because this is to the plus 1/2, that's to the minus a half. This is a half times 2. So that is going to give us 4 times z plus 8 over, downstairs, the square root of what? Z squared plus 4z. And then, what do we have? Well, this a half times 2z plus 4 is plus z plus 2. Huh. Okay. Well, I guess we're making progress. Huh. Well, what do you say? Should we do it one more time? Maybe one more time, right? It's got to work eventually. Come on, l'hôpital. One more chance, my friend. One more chance. Okay. So, upstairs we get 4. And downstairs, well, a half. Z squared plus 4z to the minus a half times 2z plus 4 plus 1. Again, we're going to multiply by, whoops, we should have said we're going to multiply top and bottom here. And here we'll do the same thing. And what do we get? Well, we get limit as z goes to infinity. And what we end up with is 4 square root of z squared plus 4z upstairs. And downstairs we end up with, well, 1/2 times 2z plus 4 is z plus 2 plus square root z squared plus 4z. And you might say, wait a second, that feels kind of familiar because it is kind of familiar. It's what we've seen before. Oh, l'hôpital! Oh, l'hôpital, you've let us down! You're not going to work. We could keep applying l'hôpital forever. And we're always going to oscillate. Oh my gosh. L'hôpital. We are no longer friends. So, wait, what can we do? Does this mean we can't do this limit? No, it doesn't mean that at all. It just means, look, l'hôpital is not the only tool. Just because you have a powerful tool doesn't mean you have to use it. Let's talk about this limit. Can we find this limit? Well, this is a limit which is blowing up. And so we go back to our old thing and say, let's pump the brakes. Let's slow it down. How fast is it blowing up? Well, the answer is it's going by this order z here. So what we're going to do is we'll multiply top and bottom by 1 over z. And if you do that and carry out the computation, some things are easy. 4z times 1 over z is 4. Z times 1 over z is 1. When you put it into the square root, you're going to get 1 plus 4 over z. So this is the let's slow things down. And now, when you take this limit, you get 4 over 1 plus 1, which is 2. So that's the actual limit. So the moral of the story is, be careful. Just because you have a powerful tool doesn't mean you have to use that powerful tool. And in some cases, it can actually get you in trouble. So be open to lots of different possibilities. Because life is full of interesting possibilities. All right, let's do another one. So, probably we should say given, so given that f of x is twice differentiable, f of 4 equals 6, f prime of 4 equals 1, and f double prime of 4 equals negative 1, then determine what this expression is. Limit as x approaches 2, x times f of x plus 2 minus 2 f of x squared over x minus 2 squared. So, first thing is plug in 2. We're going to get 2 times f of 4 minus 2 times f of 4 all over 0 squared. Well, that is 0 over 0. Okay, good. Back in business. We're going to 0 over 0, which means we can now apply L'Hopital. So this is going to be equal, give ourselves a little bit of space here, L'Hopital. Limit as x approaches 2 of what? Well, product rule. So f of x plus 2 plus x f prime of x plus 2. Then here, minus 2 f prime of x squared. But then you can do with the chain rule, multiply by another 2x. So 2 f prime of x squared times 2x. All divided by 2 times x minus 2 to the 1 times 0 to the inside is 1. Now we can clean this up just a little bit before we keep going. Limit as x goes to 2, we're going to get f of x plus 2 plus x f prime of x plus 2 minus 4x f prime of x squared all over 2 times x minus 2. Now what does this go to? Well, let's see. We're going to get f of 4, then plus 2 f prime of 4, and then here it's minus 8 f prime of 4, all over 0. Well, let's check to see if we get 0 upstairs. F of 4 is 6. F prime of 4 is 2, so there'll be plus 2 minus 8. And that is a 0 over 0, which means more work. Good. So we can apply L'Hopital again. This becomes a limit as x goes to 2. Well, what happens upstairs? F prime of x plus 2, so let's separate here, plus f prime of x plus 2 plus x f double prime of x plus 2 minus 4 f prime of x squared, and then minus 4x f double prime of x squared times 2x. All of that divided by 2. And now, you see that? Game over. Because that's not going to go to 0. So now, we don't even have to take any more limits. This equals something over 2. Well, what? F prime of 4 plus another f prime of 4. Oh, actually, that's a... Alright, plus f prime of 4 plus 2 f double prime of 4 minus 4 f prime of 4. Then this will be minus 8. Hold on. Then there's another 4 here. So that's actually going to be a lot. That's going to be 8x squared. So that's 32. Wow, that's a big number. F double prime of 4. So, well, for f prime of 4, we got 1, 2, minus 4 makes negative 2. So there's negative 2 of those. So that's negative 12. And then we have 2 minus 32. That's minus 30. F double prime of 4. So minus 30 times negative 1. So that's a plus 30. All over 2. Negative 12 plus 30. That makes 18. 18 divided by 2 gives us 9. And there we go. And so this one's not so bad. It's just a matter of we work the process. We take the derivatives, we make sure things are 0, and life is good. Life is good. All right. Well, let's do a little bit more We're getting close to the end. Okay. Find the limit as t goes to infinity of t to the 314 e to the t. Well, e to the t gets huge as you go to infinity, but so does t to a power. So this is going to infinity over infinity. So we do what we always do. L'hôpital. L'hôpital. Oh, what a beautiful thing. So we get upstairs 314 t to the 313. Downstairs, derivative of e to the t is e to the t. What does that do? Well, that goes to infinity over infinity. So what do? L'hôpital. And what do we see? Well, that's the limit as t goes to infinity. Well, here we get 314 times 313 times t to the 312 all over e to the t. And what does that do? It's going to infinity over infinity. Now at this point you're probably like, oh my gosh, what are we going to keep doing? Well, we're going to keep doing l'hôpital, but we're not going to do it without hope. See, notice what's happening to powers. 314, 313, 312. The powers go down. Every time we take a derivative, our power goes down by 1. So what do? Well, we do lots of l'hôpital in the middle here. So we're going to say, after many steps, well, how many? Well, if we take 314 derivatives on the top, what we'll get is eventually the following. Limit as t goes to infinity of 314 times 313 times all the way down to 2 times 1, but now the t is no longer there. Downstairs you're going to get e to the t. Now this number, this is a gigantic number. In fact, we have the notation for it. It's such a big number. We have this 314. That's huge. It's 314 factorial. It's way bigger than anything we'd ever have to work with. I mean, it far surpasses the number of particles in the universe, far surpasses the number of particles in every universe's universes. I mean, there's just an unbelievably huge number. And e to the t will get bigger because this is a number. And e to the t will outgrow any fixed number. So what's our limit? The answer is 0. And in fact, what this is really showing to us is the following fact, is that polynomials are much smaller than exponentials. So sometimes people will use sort of this notation. But the key here is polynomial functions grow smaller than exponential functions. So between a polynomial and exponent, you always will bet on the exponent. And the good news is if you're investing, like bank interest is exponential growth. So in the long run, it's a lot of money. Of course, you got to wait a long time. All right. One last problem. Find the limit as t goes to 0 of t squared plus 2 log cosine of t divided by t to the 4th. Well, where does this go to? Log of t equals 0. We're going to get 0 upstairs, 0 downstairs. So we can apply l'hôpital. Now, looking ahead, we might be doing a lot of l'hôpital. Do you see that t to the 4th? That says it's going to take a while to get it down to something where I don't have a t downstairs. So we're going to brace ourselves for much l'hôpital fun. All right. Maybe as many as 4. So, first time, okay, 2t plus derivative of log of cosine. Well, cosine goes downstairs. Upstairs would be negative sine, which is the derivative of cosine. All of that divided by t to the, 4t cubed, derivative of t to the 4th. Well, we can clean that up. So that's the limit as t goes to 0 of, well, I have a 2 and I have a 2 and I have a 4. Let's go ahead and cancel it, just so we keep things tidy. T minus tangent of t divided by 2t to the third. And that goes to 0 upstairs, 0 downstairs. So what do? We do L'Hopital. That becomes a limit. As t goes to 0. Upstairs, well, derivative of t minus tangent of t, 1 minus secant squared t. Downstairs, derivative of 2t cubed, 6t squared. Now, plug in t equals 0. Well, obviously, downstairs is still 0. Upstairs, 1 minus 1, also 0. So this is going to 0 over 0. So what do? Ha ha ha! L'Hopital! L'Hopital! You get a L'Hopital. You get a L'Hopital. Everybody gets a L'Hopital. All right, upstairs, what do we have? Well, derivative of 1 minus secant squared will be minus 2 times secant. And the derivative of secant is secant tangent. Now, I already have one secant, so it'll become a second secant tangent. Downstairs, 12t. All right, what does this go to? Well, it goes to 0 over 0. All right, so what do we do now? One more, L'Hopital. Once more to the breach, dear friends. Once more. Downstairs, 12. Game over, man. Game over. That's not going to give us a 0. So whatever happens, this is when it's going to happen. So now we've got to work through our derivative. So we'll have minus 4 secant t times the derivative of secant, which is secant tangent, times that other tangent. All right? Then minus 2 secant squared times the derivative of tangent, which is secant squared. And now, because we have a 12 downstairs, we're ready to write down our answer. It's 12. This term will have a tangent of 0, which means it's going away. Secant of 0 is 1, which means what are we left with? Well, that negative 2, giving us a final answer of negative 1 over 6. Probably what we wouldn't have expected, but we don't have to expect anything. We do the math. We do the math. So be patient. Watch out for other things. Maybe there's a better way. Work on ways to simplify what you're working with. And lots of fun stuff you can do with L'Hopital. All right. Mon ami, see you next time.